Picture this. You're a high schooler during the height of the pandemic, and you're stuck at home. Let's be honest, you're never going to finish your homework anyways, as if you can remember all the trigonometry they taught you. So, bored out of your mind, you pull up a video game, Minecraft let's say. Now as with any video game, the goal is to earn gold, and thankfully that's pretty easy in Minecraft. But on your quest to build a machine that makes gold out of thin air, you notice something unexpected, and that will have some surprisingly deep implications. So, how does this machine work? Well, there are these monsters called zombie pigmen, which as the name suggests is some linear combination of zombie pig and man. Each one carries a golden sword, individually containing a minuscule amount of gold, but collectively, over millions and millions of creatures, it slowly adds up. Well, where do these creatures come from? For each point in space, as long as it sits on some floor or platform, it rolls a dice, and there's a small chance that a pigman will spontaneously generate. But there are some key requirements. For one, it can't be within 24 meters of you, the player, because the game decides it's too close for comfort. On the other hand, it can't be too far away either. It has to be within 32 meters of the player. Now, you probably want to get rich quick, to speed up the machine as much as possible. How would you do that? Well, there are a number of factors, like the total number of monsters there are, the distance away from you, but the biggest factor is probably the total amount of space there is. The more space there is, the more pigmen there are, the more gold you make. So that's your goal, to maximize the total amount of space on your platform that is between 24 and 32 meters in distance. Well, the gold's what we want, but what do we have? We know that we have one degree of freedom, and that's the height of the platform. We also know that the circle's area is going to be involved, so let's write down pi r squared. And while we're at it, we might use right triangles later, so Pythagoras or trigonometry might be useful. That will of course relate all our lengths and distances, all the different variables. Let's write our two distances as concentric spheres with radii little r that we can slice at some height h. We know we want to maximize the area of our cross-section, two concentric circles, so let's say that our inner circle has some radius capital R1 and the outer circle R2. Now, how does the circle's radius change when we move our platform up and down? Obviously, if the platform is off at the two ends of the outer sphere, it's going to be very small, so we're going to focus on the middle. Let's look at our inner sphere first. We know from trigonometry that we can write capital R1 as little r1 times the cosine of some angle θ1. We can find θ1 because we know little r1 times the sine of θ1 equals to h. Take the inverse and combine the two equations, and we get that capital R1 equals little r1 times the cosine of the arcsine of h divided by r1. We can do the same thing for the outer radius, plug that into pi r squared and find where the area is the greatest. Well, plugging things in, we get that the area equals to pi times r2 squared times the cosine squared of the arcsine of h divided by r2 minus r1 squared cosine squared of arcsine of h over r1. That's a rat's nest of numbers and letters and functions, so good luck solving for anything. Well, when in doubt, plug it into Desmos. And now we have something even more confusing. Somehow it's constant. Clearly something's gone horribly wrong. Pause and ponder for a moment, see if you can work it out. Let's take a step back. Look at our algebra. We went from heights and distances to angles and back to distances again. Surely we can simplify things by skipping all the angles in trigonometry. And indeed we can by using Pythagoras. We know it's a right triangle, so little r1 squared equals to capital R1 squared plus h squared, same for r2. Plugging that into pi r squared, we can see that the area is pi times bracket little r2 squared minus h squared minus little r1 squared minus h squared. The h's cancel out, so no wonder it's constant. That means that we can put our platform anywhere we want, and the amount of gold will be the same. Let's double check if it makes sense. We know we have some cross-sectional slice of our two spheres, and if we move it either way, sure, the outer circle might get bigger, but so does the inner circle, so it's conceivable that the area does indeed stay constant. Well, maybe it's not that helpful for the gold, but it's a fun problem nonetheless. So what did we learn today? Well, first off, I guess we figured out that it's pretty easy to earn gold in Minecraft. But much more than that, what we've learned here are the skills you need for problem solving. Let's look back at what we did. First, we laid out the groundwork for our problem, namely that we want to maximize our gold output, which means maximizing the area of our platform. Then we wrote out what factors influence the area, and here there's only one, the height. That controls the radius of the platform, which in turn controls the area. Next, we used trigonometry to find how the height controls the radius, where we arrived at the arcsine-cosine equation. Seeing that the equation is too complicated, we did two things. One, we went to Desmos and saw that the area ended up constant. And two, we then took a step back and re-examined how our equation was written out. There, we realized that we can skip all the trigonometry and use Pythagoras, which cancels out and simplifies down to a constant. So, going back to the original question, this means that the area of a platform can actually change, so we can put it anywhere we want and get the same amount of gold. Now, you might look at the insight of using Pythagoras as the key step that finished off the problem, and indeed, as the famous quote goes, a change in perspective is worth 80 IQ points, but I'd argue that the other 20 is just as important, because if it weren't for the groundwork of understanding and characterizing the problem, we would have never came to this point. Recall, the first thing we did was listing out all the variables involved in the problem and how those equations relate them to each other. It might seem trivial, but it's the most powerful thing you can do because it very explicitly tells you the connection between different parts of the problem, which will organize your thoughts later on. Another thing we did was to use Desmos to get a feel for how the area changes, and that's important because it helps build intuition. Same for using graphics to visualize the cross-section of the spheres. My final tip is probably the most genuine, and that's perseverance. 3 years ago, I was a high schooler during a pandemic. I did skim my trigonometry, and I did play Minecraft. So, when this problem came up and I couldn't solve it, I asked my physics teacher, on Zoom of course, and at the time she couldn't solve it either, but she urged me to keep trying, and I always kept that in the back of my mind. 3 years later, I gave it another go, and here we are. Thank you for watching. I'd like to thank my high school physics teacher for encouraging me, both in this question and in math in general. I'd also like to thank Grant from Freeborn Brown for hosting this Summer of Math Exposition, which gave me the impetus of trying the problem again. Additionally, I'd like to thank Mojang, C418, and others for the use of assets. Check the description for a full list. Comment down below if you have any questions or suggestions, and thank you for watching.